All right, I'm going to move through these examples fairly quickly because they are similar to last year. Some might be a little bit more complicated with the algebra, but you should be able to follow along here. So a ball is kicked off a balcony with an initial velocity of 18 meters per second east. So if it's heading straight east, that means the ball was kicked off in that direction. So I have horizontal information there. I need to know my V1 is 18 meters per second east. I also am given vertical information there. If it's kicked straight east, then my V1 vertical will be 0 meters per second, and I'll put down for argument's sake. All right, the balcony is 8 meters above the ground, so I'm given a vertical displacement. I'm going to assume down is positive, so I know my delta D is 8 meters. That would be down. Determine how far the ball traveled horizontally. So we are looking for our horizontal delta D, and I put an X component there. That helps distinguish between the two. So that means I'm looking for delta D, and I'll put the subscript X. That's the unknown. Now horizontally, because acceleration is 0, and you don't need to write this in, but recall, or maybe you do for the note, acceleration is equal to 0 meters per second squared. So therefore, we only have one formula to work with here. So we need to be able to find delta dx, that's our final, and we need to find time. So we need to be able to find that time from somewhere, and you're going to get it from the vertical information because time is constant, and it's the only one that can be shared between the two columns. All right? So delta t is the only thing common. Only thing common between horizontal and the vertical. All right, so we must know one more other piece of information, and it's that inferred piece of information. It's that acceleration due to gravity. So I need to pick a formula that uses those particular variables. So the only one that will do that is delta D equals the V1 delta T plus 1/2 a delta T squared. So we know displacement's 8. We know velocity, V1's 0, so I don't have to worry about it. 1/2 times 10, and our delta T squared. So we end up with 8/5. Half of 10 is 5. Going to divide both sides by 5. Get your delta T squared. And delta T equals the square root of 8/5 seconds. So you can go ahead. You can calculate that down to a decimal. I'm not going to stop to get a calculator here. I'm okay with that. Next, then, we now know time. All right, so I'm going to put this in red over here. Square root of 8/5 of a second. Okay, and that comes from my star, so the red boxes kind of match up. Now I can go ahead and use the horizontal information here. Because I am looking for dx, I know the launch velocity was 18 meters per second, and I know the time was 8/5. So my final answer, and again, if you want to calculate it down to a decimal, you can. But that is my final answer, 18 times root 8/5. So therefore, the horizontal distance is 18 root 8/5 meters east. All right, so sometimes you need the vertical in order to determine or find the horizontal. So the next one, a child travels down a water slide, launching with a velocity of 4 meters per second right, 8 degrees up. So they are launching at an angle. So if this is the horizontal, they are launching at that angle, which is 4 meters per second. The angle is 8 degrees. The end of the slide is 3 meters above the water. So this point is 3 meters. A diagram always helps you out. Determine. So before I even answer the question, I'm going to break down my information here. So I do know my initial velocity. It is going to be the magnitude of the vector. So 4 cos 8 degrees. That's meters per second. And again, you can calculate that out. I just don't want to grab my calculator at the moment. Horizontally, I don't know how far the child will travel, and I don't know how long the child was in the air. Vertical information here, I know the initial velocity, and I'm going to assume, again, down is being positive, which means that my launch velocity, or V1, they're heading upward, so I'm going to have negative 4 sine 8 meters per second. Now, you can pick whichever direction you want to be positive. Just be consistent in your calculations. My delta D is down 3 meters, so that's why it's going to be a positive. So that's down. And this is, I'm reporting it as down because I have it as a negative number. It just reduces my confusion when I go back to plug stuff into a formula. Time's unknown, and I do know acceleration is 10 meters per second squared down. So you can kind of see a theme here. We're going to have to find that time in order to answer the question, I'm guessing. So let's read what A wants. How long was the child in the air? A part is just going to be taken from vertical information because that's the only one that has enough information to solve with. Same formula as previous. So V1 delta T plus 1/2 A delta T squared. So I know the displacement will be 3. My V1 is negative 4 sine 8 multiplied by delta T plus 5 delta T squared, half of 10. So I'm looking at this right away. I've got a sinking feeling that I'm going to have to use Pythagorean, or not Pythagorean theorem, quadratic formula to solve. So if I rearrange it, 0 equals 5 delta T squared, and now I'm going to actually break down and get a calculator. And I find I have 0.6 delta T squared and minus 3, bringing it over. So I'm going to have to use that quadratic formula to solve here. So solving for delta T, it will be negative B, so 0.6 plus or minus 0.6 squared minus 4 times 5 times negative 3 over 2 times 5. So it will be 10, 0.6 plus or minus 7.8. So cleaning that up then, so 0.6 plus the 7.8 divided by 10 gives me 0.84, so less than a second. Or the 0.6 minus the 7.8, divide that by 10, we get negative 0.72. Now, that negative answer, of course, is inadmissible. Inadmissible. So our answer then for A, therefore, child is in the air. For 0.84 seconds. B part. What does B want us to find? The minimum length the splash pad would have to be for the child to land safely. So it's just the same as the previous question. It's just worded a little bit differently. We want to know delta X. When is it? How long does it have to be for that child to safely land? Well, we know the time, or the flight time. So now we can use that information, 0.84, and we can use our delta D equals V delta T. So we know we are traveling at 4 cos 8. The time is 0.84. So our delta D, 4 times cos 8 times 0.84. We find that we have 3.33 meters to be safe. So therefore, the landing zone must be longer than 3.33 meters. So we actually don't even need it to be, it could start at 3 meter point and then go from there. So it doesn't have to go right from the bottom of the slide, although that's probably violating some code, so it's probably needed to have it that long along the bottom. So there we are. Third example. So I will get it set up and started. So a plane is doing a supply drop. The plane is traveling at 135 kilometers an hour. So we're assuming horizontally because there's no angle provided. So I'm going to jump to my information here. So my velocity is 135 kilometers an hour. Of course, you want that in meters per second, just for purposes of using gravity. So that's 37.5 meters per second. And I'm going to say he's heading right, which means my vertical information, my V1 is 0, because I'm assuming he's flying perfectly flat. I know acceleration is going to be 10 meters per second squared. That's down. The height is 800 meters, so we know how high the plane is. So that is a vertical. Determine how far from the release point the package will land. So as you can see, this example is virtually the same as the previous. We're looking for that delta x. Because V1 is 0, it makes that question a lot easier. So delta V equals V1 delta T plus 1/2 A delta T squared. V1 is 0. So we'd have the 800 equals 5 delta T squared. Dividing both sides by the 5, you get 160 equals delta T squared. So time here, 160, be 12 points, call it 12.6 seconds for impact. So therefore, we want to know that horizontal distance dx. We now know the time for the drop. So delta D equals VT. So the velocity then would be the 37.5 multiplied by 12.6. So when the plane hits the release lever to let that package drop, it's going to land 472.5 meters to the right or away from the plane. Therefore, 472.5 meters from point of release. All right. So 3 examples are pretty much identical. I want to do a little bit of variety here. Just going to take a look at the golf ball question. Virtually the same question, except for maximum height. So what I'm going to do in the next video, I'm going to take this one up. If you're feeling confident about projectile motion, you'll know it once you start into the homework. So you don't really need to watch the 3rd video. If you want to see the 3rd video, just to make sure you have an extra or 4th example, because there's a question about finding max height, you're welcome to quickly scan through it. But that's what I'll do. I'll tie it up, that last example. If you're good, go ahead and start.